Alright, morning everyone. We'll be starting class in 1 to 2 minutes time. Alright, good morning everyone. And today's lecture is going to be focused on the use of the spectrum analysis. And we're going to be looking at, in particular, what happens when we zero pad our discrete time signal and we convert that into the frequency domain representation. What is going to be the effect of the signal in frequency, as well as what happens when we incorrectly sample the signal and then we transform it into the frequency domain. And we also want to observe the effect that happens when we do that, and how can we mitigate that particular effect by using windowing techniques to ensure that we can get rid of or reduce unwanted frequency components due to that incorrect sampling. So typically we'll have some input signal here, and inside of the signal we'll have some sort of components here that we just don't want altogether, because there may be a result of noise or some other sort of background signal that was interfering with the pure signal that we actually do want. So the question is, in having this signal here in the time domain, how do we extract the actual data that we want from the signal? And we can see here, this signal in particular was a 200 Hz signal sampled at 1000 Hz. So what we observed so far from all the lectures that we've done is that we would have started with a continuous time signal x of t. We would have sampled it to get the discretized time version x of n. We'll then do the fast Fourier transform with the FFT on x of n to get into the discrete frequency domain, getting our representation x of k. Then do some spectrum analysis here in order to extract out the information that we want and get rid of the information that we do not need, formulating a next x of k signal here. This is either done visually or automated, automated being that is a programmatically applied technique in doing spectrum analysis. We then filter the signal to get rid of any unwanted frequencies in particular, and we end up with x of m, which is the signal that we do actually want. We then do the inverse fast Fourier transform to convert from the frequency domain, this being the discretized frequency domain, back into the discretized time domain, being y of m, because this is matching up with our x of m signal. And then we do signal reconstruction to get this back into continuous time domain, y of t. Y of t being our continuous time output signal. So this entire process is normally what happens when you do any sort of DSP analysis on a continuous time signal, and you're required to get back the output in continuous time. Remember, the reason why we do this analysis in discretized time and discretized frequency is that we don't have to build any complex circuitry in order to do this. We can just basically use a programmable chip or any sort of digital system that will allow us to implement our filters digitally and do our spectrum analysis digitally as well, but saves on time and cost in particular because we can reprogram those chips for multi-purposes. So, in assessing the frequency content of the signal for spectrum analysis, this actually gives us an idea of which frequencies do we want and which frequencies we don't want. And that's important. That's important because the FFT does this for us. Now, in doing some considerations for actually doing the FFT and doing the samples for converted or continuous time signal to a discretized time signal, we pay attention to the Nyquist frequency, being that the sampling signal's frequency must be more than equal to twice that the bandwidth of the signal's frequency. The bandwidth here being the highest signal frequency of the continuous time signal. And we also watch the frequency resolution, determined by the number of samples that we're going to use in order to represent our signal from continuous time into discretized time. And we also saw that the frequency couplets, they were spaced, we obtained bin frequencies noted by delta of f, which was the sampling frequency divided by the number of samples that we took. So in this example here, if we had a 5 kilohertz bandwidth signal, and we need to obtain our sampling frequency and the number of samples to get a resolution of 10 hertz, the resolution of 10 hertz here being how accurate our signal representation is going to be in discretized time. We know that the sampling frequency here, f of s, must be twice that, at least twice that of the bandwidth signal frequency. So that's going to be 2 by 5 kilohertz, which gives us at least 10 kilohertz. So we'll use the bare minimum here for our question, 10 kilohertz. The resolution here, which is 10 hertz, is given by delta f. So if we rearrange our equation here, because we're solving for n, we just put delta f or the denominator instead. So we have 10 kilohertz divided by 10. This here being kilohertz as 10,000, so we get n being at least 1,000 samples that we need to take. Because the FFT here operates on powers of 2 for the number of samples, we go up to the next available power of 2. So for example, if this here calculated to 1025 hertz, we will not use 1024 hertz. Sorry, we will not use 1024 signals. So mixing up myself, let me repeat that. If n here being the number of samples was calculated to 1025 samples, we will not use 1024 samples. We'll go up to the next available power of 2, which will be 2048 samples accordingly. We cannot go down. We must always go up when we're using the FFT, for the number of samples being to the closest power of 2 possible. So let's say if we had n being equal to 10 samples, for the FFT usage, we'll have to go to the next available power of 2 that is higher than the 10 samples that we calculated for n. That means we'll be using 16 samples for our FFT. Now, in that question there, we use the bare minimum for our Nyquist rate, being 2 times the signal's bandwidth frequency. If we're going to be sampling at higher than the Nyquist rate, that means you're going to need more samples for the required frequency resolution. You're going to have to balance your sampling frequency and your frequency resolution to figure out, okay, how many samples do you actually need to maintain your memory requirements, because you can't have so much samples without impacting on the amount of memory that you actually physically have. So you're going to have to make a decision on what's going to be your system storage versus your required frequency resolution, as to how many samples can you actually use in particular, and what's going to be the bare number of samples that you actually need to use within your system itself. Alright, give me 1 second. have to deal with one thing here, so I'll be right back. Alright, I'm back here. Sorry about that. Hopefully I won't get interrupted for the rest of the session. If I do, I'll just tell you guys accordingly and switch to the be right back screen. Alright, so let's continue from where we were talking about here. Right, so what I was mentioning here on this slide is that you need to make sure that you balance your required sampling frequency and your frequency requirements, which is going to give you an idea of what your system storage is going to be. So I'm balancing the sampling frequency here and frequency resolution, meaning how accurate you want your signal reconstruction to be. This will match back to the least amount of samples that you required for your system storage, and then the amount of samples that you would actually want to balance your sampling frequency and your frequency resolution. And this is important because if you're dealing with systems that have very limited memory, you'll have to pay attention to how many actual samples you can use and what's going to be the actual frequency resolution that's going to affect the accuracy of your signal representation. So let's watch effect here if we have yeah, it's a design choice. So the design choice is going to be limited by hardware factors, and most of the times it's always going to be memory. So once you have that memory limitation, you have to figure out, okay, what's going to be your required sampling frequency, which is something most of the times it can't really change, but you'll know what's going to be the minimum sample frequency because that's going to be twice that of the signal's bandwidth. And then you can be like, okay, maybe I want to sample a little bit higher than that sampling frequency. But at the same time, you also need to figure out, okay, what's going to be my frequency resolution, which is going to determine the amount of samples that you take, and that's going to be stored in memory. So you need to balance the required sampling frequency and the frequency resolution to match back to the amount of samples that you can actually store in memory. So yeah, at that point, it's going to be a design choice that's going to be limited by the hardware that you have. So let's watch an effect here. What happens when we actually zero pad a signal as a result of having samples that's going to be less than the required FFT number. In this case being that, let's say, well, we have 4 samples here which would actually match up, but let's say if, just for argument's sake, if we had 5 samples and then we had to get up to 8 samples to perform our FFT, one way of doing this is that we can zero pad the signal, so we add zeros to the end of the signal until we hit the required power of 2. But what we're going to observe here is that what's going to be the effect in frequency when we actually do this zero padding upon the signal itself. So 2 ways you actually could get to this sort of number for your FFT, meaning to the closest power of 2 possible, is that you can actually increase the number of samples that you take to get up to that number, or if you can't do that, you can just zero pad the signal up to that number, being to a power of 2 that's required for you to perform the FFT. So when we actually zero pad our signal here, and in our case we had our signal here being originally 4 samples with magnitude 0.5, but we said, okay, let's zero pad up to the next available power of 2, so we're going up to 8 samples, being 2 to the power of 3. When we do the FFT of the signal here, we see that we get a lot of zero components in particular, as well as we get some other frequency components as well, being this 0.5 here, minus 1.2071i in particular. And because of this, when we zero pad here in particular, that's why we get these additional frequency components, because now we have extra samples in our signal itself that's going to be factored into our FFT calculation. Similarly, let's say if we went up to 16 samples and we zero pad up to that and we perform the FFT, we can see here that the original signal components that we had if we only had 4 samples would have been let's go back one more slide. That'll be 2000, right? Because this is a DC signal and there's no AC frequency components. But when we zero pad up here to 16 samples, we see here that it's in between the 2000 here, we have more frequency components being added in between. And this is going to be a result of us zero padding altogether. So in zero padding your signal, you do add some additional frequency components that tend to be unwanted regardless. But this is going to be the effect of actually doing zero padding upon your signal. And it's possible for you to actually eliminate these unwanted frequency components by actually performing filtering, because when you do watch these in frequency, you can tend to see like, okay, this is going to be at like a first, second, and third harmonic, and you can just filter out from anything before the first harmonic to get your original signal frequency components, and you'll pretty much be fine once you do that technique. So just pay attention to when you actually start zero padding your signals. You want to get frequency components in between your true frequency components of the original signal, which tend to be unwanted in particular. And the more you zero pad, the more you're going to get more of these components in between your original frequency components. So in the comparison of both of these spectrals here, where we had 8 samples and 16 samples here, where our original 4 sample signal was 0 pattern, we see here that this signal component here, the signal frequency component here that was added because of the 0, also matches back here in particular. And because we had added more zeros for the 16 sample here, we see here that we have more unwanted frequency components being added, but we still have this same frequency component from the 8 sample FFT. That's going to be matching up here accordingly for each one of these. So these red arrows there indicate the additional unwanted frequency components that have been added because of the amount of zeros that we added to be extra onto the FFT. Now, when we actually visually watch this in particular, in the frequency domain, the 8 sample FFT here gives us an idea, okay, be like, alright, this is the general shape of our signal. But the 16 sample here gives us a better idea of what the actual shape of the frequency signal is going to be, because of those unwanted 0 components in particular. So, 0 pattern technically gives you a better visual representation of what the frequency components are going to look like if you had it in continuous time. Sorry, in continuous frequency. So 0 pattern, as a result, even though you do get some unwanted frequency components, it increases your frequency resolution by giving you a nice, more accurate reconstruction in the frequency domain. So this sort of effect is what we refer to as the picket fence effect. And the reason for this being that, remember that fast Fourier transform that we use in the FFT is an approximation to the DTFT that we saw in the previous slides. In the previous lectures. And when we did the DTFT, we saw that we obtained a continuous spectrum, but the FFT here will give us a discretized spectrum. So because the FFT here has been an approximation to the DTFT, the more samples you basically have, you get closer and closer to what the actual DTFT continuous spectrum looks like. And the trade-off is, because you have more samples, you require more memory. So you just have to balance that accordingly when you have your hardware decisions to make and so forth. Each frequency impulse that we saw there, they will occur at the sampling frequency divided by the number of samples that you have. And like I said, it's referred to as the picket fence effect, because it looks like a picket fence. And if this f of s divided by n does not correspond with an actual signal frequency component, basically you wouldn't see it in that frequency plot that we just saw. So technically, what that means is that if you have a frequency component that is going to be in between two successive frequency bins, being f of s divided by n, where we have k and then k plus 1, so two successive frequency bins, if you don't have anything sampling in between those two, you're going to be missing that frequency component altogether from your original signal. So that's why the frequency resolution also is somewhat important for you, to make sure that you don't miss critical frequency components from your original signal that you're dealing with. Now in sampling the continuous time signal, typically you could have done that in two ways, right? You could have watched the signal periodically at some rate and you could have formulated your sampling frequency, or you could have taken the fixed number of samples of that signal, formulating your sampling interval instead. You could have done a mixture of the two as well to match up the sampling frequency and the sampling interval. That's fine as well. But typically you tend to use one or the other when you're sampling a continuous time signal to get a discrete time signal counterpart. So if we sample that 2K signal here at 10 kilohertz, basically that gives us the sampling frequency here being 10 kilohertz. If we took 256 samples of it, being 256 samples of that 2K signal here, these 256 samples at 2 kilohertz refers to our sampling interval instead. Now, in having a duration of the sample interval, this actually creates an observation period where we only can observe those samples in particular from the continuous time signal. And that observation period is what we refer to as our sample window. So the pros and cons of using either one of these processes here is that when you use the sampling frequency method, this is good for periodic signals. So that way you can make sure you get a nice clean reconstruction altogether. So using a sampling frequency method here, you tend to make start with knowing what's going to be the periodic frequency of your original signal. And then you say, okay, you just go up in integer multiples of that periodic frequency. When you're dealing with aperiodic signals in particular, you'll tend to use sampling intervals instead, because an aperiodic signal, there are so many frequency components inside it, you don't know where to begin to obtain a sampling frequency. And even let's say, okay, you want to use the highest signal frequency in that aperiodic signal, and you get your sampling frequency, there's a high chance that you will miss some other signal frequency components inside there because of the mixture of frequencies that's going on in that aperiodic signal. So typically when you deal with an aperiodic signal, you want to use a sampling interval instead, being, okay, we would take so many samples here to try and mitigate all those frequencies that's going on inside there. We try to get at the best possible approximation for that aperiodic signal. So sampling frequencies are used typically for periodic signals. Sampling intervals are used typically for aperiodic signals. Whereas the sampling frequency gives you a nice clean reconstruction once you know what's the original signal frequency. The sampling interval here, because we're using them with aperiodic signals, it does not give you the best possible reconstruction because you're trying to mitigate that approximation effect because of all those frequencies there, that aperiodic signal. And we're going to be observing what happens in the next few slides when we use the sampling interval process here, and what's going to happen when we do coincide with the signal frequency. So in using the sampling interval process, that means that you're only going to be observing the signal for a fixed amount of time to get that amount of samples. And that fixed amount of time referred to as our observation period, we refer to this as a sampling window. So the most basic sampling window that you've been introduced to so far is the rectangular window. Basically, where our rectangle here has a start time and a stop time, and just basically has a flat magnitude of 1 here to sample out all the signal that is required between these two time points in particular. So that comes like if we just take any arbitrary continuous time signal here, and we multiply by rectangle, and we set our start time and stop time, meaning, okay, we just want from here to here in particular from that signal. So we just extract out that signal accordingly in between that start and stop time by doing the multiplication of these two signals here. Now, this rectangle window here basically imposes a sampling window upon that original signal that we had here to begin with. So the sampling window here means, as a result of that rectangular window that we just did, or that rectangle signal, that's equivalent to that multiplication that we just did of the original signal by the rectangular signal. The assumption that we make when we're using our sampling window technique is that you need to recall that the FFT, the DFT, and the DTFT assume that that original signal was periodic with a period of n, where n here was giving us the amount of samples that it was required for us to maintain that periodic property. So in performing the DTFT, the DFT, or the FFT, that means you always be imposing a period of n regardless of the actual period of the signal. So let's examine what happens when we actually do this, and what's going to be the effect when we don't coincide with that period n. So if we have our original signal here, and our sampling window happens to coincide with the period of the original signal, that's nice. That means we get a nice replication of the original signal when we actually try to do the reconstruction from the frequency domain back into the time domain. So, sorry, when we go from the discrete time domain back into the continuous time domain. So once that sample window coincides with the actual signal frequency, everything is fine. You get a nice perfect reconstruction of the original signal. However, so yes, you also get an accurate spectrum because of the same sampling window coinciding here with signal frequency. However, if the sample window here does not coincide with the signal frequency, meaning that you don't happen to coincide with period n, your replicated signal here, as a result, is not going to be the same as the original signal that you had. So you lose some information because of that incorrect sampling window size. And that means when you reconstruct your signal accordingly using this sampling window, you get some discontinuities in the signal itself. And as a result, you get an inaccurate spectrum when you actually perform this into the FFT. So let's watch this on an actual practical signal to see what happens. So we have a 1000 Hz signal here that's going to be sampled at 8000 Hz and 7000 Hz, but we're going to try and take 8 samples of each of these to see what happens. So for our first indication, when we try to figure out, okay, what's going to be our frequency resolution here, we take the sampler frequency and divide by the number of samples. So delta F1 here is going to be 1000 Hz, which coincides with the signal frequency that we started with. So that's nice. We're going to get a nice clean reconstruction here. And the reason for that is that the signal frequency bins are going to coincide with our actual signal frequency here, giving us that nice clean reconstruction in particular. Yes, there will always be discontinuities when you're dealing with aperiodic signals. The cases where there won't be any would be when you're only dealing with periodic signals in particular, because it's a lot easier to analyze a periodic signal than an aperiodic one. So for our second signal here, and we're going to calculate the frequency resolution, being delta F2. We take the sampling frequency here, which is going to be 7000 Hz, and divided by the number of samples that we are required to take. And we can see when we do this division, we get 875 Hz, which does not match back to the signal frequency that we would begin with. So these signal frequency bins here, as given by our frequency resolution for the 7000 Hz signal, they don't correspond to the original signal frequency, so you're not going to get a nice clean reconstruction altogether. And as a result, when the bins here don't correspond to the signal frequency, when you perform the FFT on both of these signals here, it ends up spreading the frequency information as a result. And this is what we refer to as spectral leakage when we have this spread of frequency information. As a result of these signal frequency bins here not matching back to the original signal frequency itself. So in our first instance here, when we perform the FFT of the signal, and we have the signal frequency bins matching back up to the actual original signal frequency, so that's being here the 8 kHz sampling that we just saw, we get a nice clean spectrum altogether. So we get it at our 2 point peaks here in particular. And everything else in the signal is just going to be 0 because we know that the signal was sinusoidal in nature, being a sine wave. However, when we had the 7000 Hz signal here, and we had that spectral leakage as a result of the signal frequency bins not matching back to the original signal frequency, we see here, instead of getting this nice clean spectrum, we get a somewhat curve effect here. And this is going to be a result of the spectral leakage effect that we just now observed in the previous slide. And we can see here, another way to analyze this is that the Nyquist frequency does not match back up accordingly. So in order to minimize spectral leakage, we can use specially shaped windows instead. Now, please note I said minimize, not eliminate, because there are cases, like I said, when you're dealing with aperiodic signals, you will have to use sampling windows, and you will get spectral leakage, and you cannot eliminate it. You can only try to mitigate the spectral leakage effect. So by using specialized windowing functions, you can mitigate the spectral leakage effect to the point where it does not affect your signal processing entirely. So in the few previous slides, we saw that when we did use W of n here being our window function as a rectangle function, this wasn't actually a good approximation for mitigating our spectral leakage effect, because of the shape of the rectangle window having those sharp transitions for start and stop. Those generated additional frequency components, which we typically try not to have as a result of using the windowing function. So instead of having that sharp start and stop because of the rectangular shape, we might want to have a more gradual shape instead for our window functions. The reason for the spectrum of the rectangular window, why we have those unwanted frequency components because of that sharp start and stop, when we did the frequency analysis of the rectangular window, we saw that we got the sync function instead. The sync function itself, when we watched it, let's say we're going to watch it a little bit closely, we had the main lobe here representing our centralized frequency, but then we had a series of side lobes here as a result. Each one of these side lobes here refers to our sidebands or harmonics of the signal. And you can see here that each side lobe here has an associated magnitude. Because these magnitudes here are somewhat high in nature, well, I mean, in comparison to the main lobe, they're not as high, but they're still somewhat noticeable. These generate the unwanted frequency effects as a result. So this will be like, okay, this is your centralized frequency. This is going to be your first harmonic, second harmonic, third harmonic. The first harmonic has some magnitude, the second harmonic has some magnitude, and so forth. So that's why you get these unwanted frequencies, in particular when you use the rectangular window. And when you're doing the analysis here, we refer to this as the relative side lobe attenuation. So you try to make sure that the relative side lobe attenuation here tends to be pretty big to mitigate those unwanted frequency components, because you want the magnitudes of each one of these harmonics here to be as small as possible. So your practical windowing functions that you want to use it instead of that rectangular window, you want to make sure that they're tapered towards the edges of the window, and that will reduce the amount of sample contributions close to the boundaries of the windows as well, and will reduce discontinuities and reduce spectral leakage in time. If you want to do a little more analysis of it, you can actually use MATLAB, and you can get all the specialized windows using the WinTool command to see what sort of windows you can actually use for sampling of signals in particular. So we're going to observe a few different shaped windows here, and what's going to be the frequency effect when we apply it upon any general signal in particular. So our first example here is going to be the triangular window, which is given by this W of k equation 2n minus k plus 1 divided by n, where k goes in between n divided by 2 plus 1 and capital N. K here being the amount of frequency components that you require. What this means is that you get a nice triangular shape instead. But as a result, even though we're doing an 8-point triangular window here, the maximum amplitude here will not be 1, and the minimum value here will not be 0. So that means coming towards your centralized frequency, you won't get the same maximum amplitude that you do required, and coming towards the edges of the windows, you won't get the same minimum amplitude required. If you increase the number of points, however, so instead of an 8 point, you go to a 64 point, you can get the maximum amplitude and the minimum values going. The maximum amplitude will go to 1, but the minimum value will go close and closer to the 0 accordingly for the triangular window itself. When we transform this, so we're going to watch a 16 point here, and we transform this into the frequency domain, you can see here that the centralized frequency maintains a magnitude close to 1 as possible, but the side lobe frequencies here are heavily attenuated. So, in comparing this to the rectangular window when we did it on our sinusoid signal, and the triangular window here, we see that the rectangular window here, we had these unwanted frequency components here being generated, but with the triangular window, we only have here and here having a slightly higher magnitude than here and here when we use the rectangular window. When the centralized part here, you can see that these unwanted magnitudes are now being mitigated as a result. And this is due to the shape of the triangular window itself. So the triangular window is good for mitigating the signal frequency components around the centralized frequency, but coming towards to the ends here, it's going to introduce a little more slightly higher magnitude. The advantages in the triangular window is if you want to focus only around the centralized frequency, it is very useful. But for certain side lobe frequencies here, you want to get some slightly increased magnitudes as a result. So because of those non-zero endpoints, that's why you get some discontinuities as a result, as we just observed in the previous slide. And because you don't get the magnitudes matching back up, because you get the maximum amplitude being close to 1 and the minimum magnitudes not going as close to 0 as possible, you lose some accuracy as a result because of that. So if you're trying to use a triangular window in particular, you want to make sure that you want to change those n values and set them to 0, and then perform the triangular window as of such. So you will try to, as a result, get rid of the unwanted signal magnitudes at the ends of the signals, whereas you can still mitigate the unwanted signal magnitudes closer towards the centralized frequency of the signal itself. Now, there are other types of windows that you can use that will have a nice gradual effect instead of that sharp edge that we saw for the rectangle, as well as the triangle window does have a linear edge as well. So we can use what we refer to as the Hamming window here, given by this W of k equation, which is 0.54 minus 0.46 cosine 2 pi k divided by n minus 1, k being the frequency components, n is the number of samples. And at first glance, this still looks somewhat like the triangular window, but let's increase the number of points to see what it actually looks like. I can see here that it's a nice curve instead, where we can get an actual maximum amplitude of 1 and get as close as possible to the zeros for the ends of the signal. And analyze this in the frequency domain. You can see here, we maintain the centralized frequency, but the side lobe frequencies are very heavily attenuated. So this is very useful in particular for mitigating side lobe frequencies here because of this heavy attenuation. In comparison to the rectangular window and our Hamming window, we can see here the rectangular window has those sharp effects here, And the hammer window here has that nice gradual change. So I'm going to observe what happens when we apply this into our sinusoid signal. And can see here that the centralized frequency is heavily mitigated as of such. The side lobe frequencies, because of the shape of the graph, we tend to have a little bit of additional magnitudes, but we still make sure that coming closer to the 1000 Hz and the 7000 Hz, we try to get as close to as possible as the original signal frequency spectrum as it is. So we do have a little bit of unwanted signal magnitudes coming out towards the ends. So, but closer and closer to the centralized frequency, we get that mitigation that is required. In comparison to the triangular window that we just now observed, we can see here that yes, the centralized part is more mitigated as such, but these sides here, for the hammer window, it's higher in magnitude in comparison to the triangular window, and that's because of that curved shape instead. There are also variations of that hammer window, which is referred to as the Blackman and the Blackman-Harris window. And all that does here is basically adds additional cosine components to the end of the original hammer window and just modifies the constant components in front in particular. But you can see here, in this particular case, the side lobe frequencies are very mitigated. There's no ripple effect that we just observed, it's just flat lines accordingly. And then for the Blackman-Harris, we can see the same thing happening as well. We get that nice flat line. Now, one thing to note in particular, once you keep on adding components into your win-win functions, is that the width of this centralized frequency here is going to increase accordingly. So in this particular case, we can see that it's going to be between 0.2 and 0.4 for the normalized frequency. But when we add this additional cosine component, we can see that the width here goes closer to 0.4 for the centralized frequency. So that's an effect that you want to observe when you're dealing with windowing techniques. The more components that you have, that means that the centralized frequency lobe width here and frequency is going to increase accordingly. You will get some heavy mitigation for your side lobe frequencies, but as a result, that means your centralized lobe here is going to increase. So whereas, let's say, if you had this the first harmonic occurring at, let's say, 0.2, you will get this magnitude here accordingly. Then let's say the second one was going at 0.4 here, you get heavy attenuation and so forth. So that's why when we're observing the windows, that's why we have these magnitudes here being higher, because of the width of the centralized frequency lobe increasing as a result. So just in concluding what we discussed here for the windowings, that spectral analysis and the spectral windows here are basically just approximations. In order to just improve the approximation, we increase the number of samples, or we try to make sure that we use the windowing techniques to mitigate the spectral leakage effect. In limiting the number of samples that we take for our spectral analysis, that results in spectral leakage. And we reduce that effect by using specialized spectral windows known as the Hamming window, the triangular window, sometimes the rectangular window if it can't be avoided, and so forth. So, just to give you an idea, if we had a 200 Hz signal here being sampled at 600 Hz, but it does not coincide with the amount of samples that we require, meaning that it will be sampled at 1 here and -1 and so forth, this results in spectral leakage entirely. And if we perform the rectangular window and the hammer window on this signal, we can see here that the rectangular window gives us the shape of the graph here in the frequency domain, meaning that we have these sharp transitions here as of such. But the hammer window mitigates some of the sides here, but coming towards the center, we're going to have increased magnitudes here. And at the centralized part, we see here in particular that it reduces as a result. We also can observe here is that for the rectangular window, the magnitudes here are 1 to 4, but on the hammer window here, the magnitudes here are between 0 and 2. So the magnitudes are basically mitigated as a result, but the general shape of the graph is going to be somewhat similar because of that curved shape of the Hamming window. Alright, so that basically brings us to the end of our spectral analysis lecture with all the windowing techniques and so forth. One thing to note though is that if a question does come on using the windowing techniques here, we will give you the window function to use in particular. And when we start doing like problem set 2b or problem set 3, you will get some practical examples of how these windows can be applied to actual signals and how you can actually obtain the required signal as a result of multiplying the two signals entirely. So you will get some experience using these windowing functions as well. And you will also see how we can actually programmatically create these windows functions using MATLAB or Octave, and how to do the analysis in MATLAB and Octave automatically for you to see if you're on the right track and so forth. Just recapping a little bit, remember the reason why we have spectral leakage is because we will end up using a sampling window for aperiodic signals, and that imposes a period upon the signal itself. And once that imposed period does not match back to the actual signal's period, we're going to get spectral leakage as a result. You can't help that spectral leakage, it's going to happen regardless. So, but what you can do is mitigate the effect of spectral leakage by using specialized window functions instead. So instead of using a rectangular window, you can use a triangular window or a Hamming window to mitigate these. And because of the shape of the windows, that means that you will tend to try and constrain the information around the centralized frequency, but you're trying to heavily mitigate the side lobe frequencies instead. However, as you introduce more and more components into the windowing function, the width of the centralized frequency lobe is going to increase as a result. So in this case, with our Hamming window, the width here was going like about 0.2 of the normalized frequency. But when we went to like the Blackman window, we can see that the width here went to 0.3. And then for the Blackman-Harris, this width here went to 0.4. And as a result of this increasing width of the centralized frequency lobe, that means that, backtrack a little bit here, that those first and second harmonics that we have, we're now going to have a magnitude that's going to be associated with them as a result. But the centralized frequencies here are going to be heavily mitigated, and you can get as close as possible to the actual centralized frequency components if the signal did not have any spectral leakage whatsoever. We also observed that in comparing the magnitudes of the rectangular window and the Hamming window here, we saw that the magnitude of the rectangular window was in between 0 and 4. But the Hamming window here, the magnitude was in between 0 and 2, meaning that each one of those windowing techniques, you do reduce the magnitudes as such, but the shapes of the graphs are going to be entirely dependent upon the shape of the window itself. That's one thing to note in particular. You will get a reduction of magnitude using the different specialized windowing functions, but as the central frequency lobe increases, as you get closer to your side frequencies here, you will get some increased magnitudes approaching towards the centralized frequency as a result. Alright, so that brings us to the end of today's lecture. Are there any particular questions? Slide 21, let's go back. See where that was. Oh, okay. In this slide in particular, I'll get back to you on this one. I think the x-axis here is wrong. It's supposed to be between 0 and 8,000 hertz instead. So this should actually be in between 0 and 8,000, but let me get back to you on this. I want to make sure and check this back accordingly before I actually give you an answer regarding this. But typically, it's supposed to be that when you do the frequency domain representation of the signal, you sort of get in one impulse here and the next impulse here, everything else is going to be 0. But let me check back the x-axis here in particular. So I'm going to put a note here on the slide to check this back for you. Check x. Oh, for these graphs, so this basically, in this particular example, we just said that this was a sinusoid graph, this being a sine signal. So that means when we applied it, it would be 2 pi by the original signal frequency here by n divided by our sampling frequency. So abstracting that, that means here that our equation here was basically sine 2 pi fn divided by fs. Oops, hold on. F n and n here was number of samples. F of s was sampling frequency. What these graphs here represent is when we actually do the FFT of that x of n. So that's why I need to verify this x-axis. So I'm going to have to replot the FFTs for these and make sure that the x-axis values here were correct in particular. Typically, when you actually are given these sort of questions, we don't actually ask you to plot the equation for x of n. And you'll see this in the problem set is that when we give you these sort of questions, we give you the x of n signal being a vector of values, and then we might give you the w of n equation to get, okay, what's going to be the vector of values for this w of n, and you just multiply those two. No, the number of samples do not represent the y-axis. The number of samples is going to be that n in the 2 pi fn inside the sign. The y-axis there just goes to gives us the magnitude as required from our original signal. Like I said, I'll just review the slide in particular and make sure everything here was correct on the slide. Alright, any further questions? It doesn't look like we have any further questions, so if there are any further questions, feel free to leave them down in the comments below or directly email us of such. Wednesday's class, we're going to be doing a little more into spectrum analysis and its effects. Now it can actually be applied to actual some real world signals as of such. I know I did upload problem set 2a for you guys to do, however we'll be doing problem set 2a next week instead. I need to go back into problem set 1 in Wednesday's lecture because when I was doing a particular question my explanation of it was wrong, so I got a request as a comment on one of the videos to redo the explanation for that. The uploaded solutions on my learning does have the correct explanation, but like I said, I'll have to redo the explanation of this. I'll be doing that in tomorrow's session after we finish the lectures in particular. So we're not going to be doing problem set 2a sorry, I said tomorrow. On Wednesday's lecture. After Wednesday's lecture, we'll be redoing a particular question in problem set 1. We're not going to be doing problem set 2a. We will be doing that next week, Wednesday instead. Once we also complete the material required, we will upload problem set 2b as of such, and we will be also doing that accordingly in the future sessions as we keep on going and so forth. Alright, so until Wednesday's session, take care, be safe, and I will see you guys soon. Later.